Welcome to the Chemistry, Biology and Math Revision Hub. Today we're doing the Pearson Edexcel International A-Level Chemistry Unit 1 for October 2022. Let us begin with the first question. Question 1 says, which mixture results in a displacement reaction? Here we can see iron and copper 2 sulfate. Of course, this is the displacement reaction. We know iron is more reactive than copper, so it is going to displace it from its compound, forming iron sulfate as well as copper. So this is a displacement reaction. If you look at B, this is lead to nitrate. When lead to nitrate reacts with sodium iodide, we're going to form lead iodide, which is going to be a precipitate, so this is a precipitation reaction. When hydrochloric acid reacts with sodium hydroxide, a neutralization reaction occurs. And when you react zinc and magnesium sulfate, because magnesium is more reactive than zinc, there will be no reaction. So the answer here should be an A. This is the only displacement reaction. When we go to question 2, they say which mixture results in a precipitation reaction. So when we see dilute sulfuric acid reacting with potassium hydroxide, that is not precipitation. Iron with calcium chloride, not precipitation. Actually, the only precipitation reaction is when silver nitrate reacts with potassium bromide, because here we're going to form silver bromide. And of course, you know, all halides of silver are going to be precipitate, so the answer should be a D. Moving to question 3. Question 3, an atom of nitrogen, they've given you the atomic mass as well as the atomic number, forms a nitrite ion which is N3-. What are the numbers of protons, neutrons, and electrons in this ion? Because the atomic number is 7, the number of protons is going to be 7, and we see the mass number is 15, the neutrons are going to be 8. However, when we see 3-, it means it has gained 3 electrons, so 7 plus 3 gives us 10. So the electrons are going to be 10, so the answer is going to be a C. Moving on. Question 4. What is the total number of orbitals in a sulfur atom which contains at least 1 electron? A sulfur atom containing at least 1 electron should have 9 orbitals. I tried to write them here so that you can see. Because here they said at least, it means 1 or more. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are 9 orbitals that contain 1 or more electrons. So the answer should be a D. Question 5. Which structure has the name E2-bromo-3-chloropentoene? Because we have a pentoene, there should be a carbon-carbon double bond on carbon 2. And then because we have, of course, this is an E, it means it's going to be on opposite sides, as we can see that and that. This is out. And we can see the potentials could be that, and A. However, we see carbon number 2, so the answer is going to be A because it's going to be the bromo on carbon 2 and the chloro on carbon 3. So in this case, this is going to be 1, 2, 3, 4, 5. So bromo is on carbon 2, chloro on carbon 3. We have a double bond on carbon 2, and these are on opposite sides, creating an E structure, so the answer should be A. Moving on. Question 6. The partial oxidation of butane in the presence of a catalyst has been investigated as a possible source of hydrogen. This is the reaction. They say what is the most significant hazard associated with a pollutant, carbon monoxide? Carbon monoxide is a toxic gas. So among all these answers, this is the only one that talks about toxicity. The others are talking about acid rain, absorbing infrared radiation, the main cause of the ozone layer depletion. This is also out, so the answer is going to be a C. A mixture of 40 centimeters cubed of butane and 20 centimeters cubed of oxygen reacts in a sealed system to form carbon monoxide and hydrogen. What is the total volume of gas in the system at the end of this reaction? So here I rewrote the equation for the reaction as it was given previously. And then since we have 40 centimeters cubed of butane, I wrote them here. We have 20 of oxygen, which I wrote here. When we look at the mole ratio, they should react in a ratio of 1 to 2. Meaning 20 centimeters cubed of oxygen should require 10 centimeters cubed of butane. However, we have 40. It means 30 centimeters cubed of butane will be in excess, and therefore they will not react. So it means at the end, these 30 centimeters cubed of butane are going to contribute to the total volume of gas present. So I wrote them here. Now we can confirm that oxygen is a limiting reagent, and so I'm going to use a volume ratio of oxygen. So using the volume ratio of oxygen to find the volume of CO2 produced, it's going to be 4 divided by 2 times 20, which gave me 40 centimeters cubed of carbon dioxide. And then the volume of hydrogen is going to be 5 divided by 2 times 20, which gave me 50 centimeters cubed of hydrogen. Now to find the total volume of gas, I have to add that, plus that, plus that, which gave me 120 centimeters cubed, and my answer here should be a D. Moving on. Question 7. Octane, which is that, reacts with bromine in the presence of ultraviolet radiation. They ask what is the role of ultraviolet radiation in this reaction. The role of UV is to cause the breaking of the Br-Br bond only. It does not participate in the breaking of the other bonds, so the answer here should be an A. In part B, one of the steps of the reaction is shown. This one here is a propagation step. So they say what is the name of this step and the type of bond breaking that takes place in the bromine molecule. So this is going to be a propagation step because we see one free radical is reacting with a non-radical, producing a different compound as well as a different radical. However, this bond here is going to break homolytically, so the answer should be D. The step is propagation, and then the bond breaking with bromine is going to be homolytic bond breaking. In part C, what is the overall equation for the reaction of octane with bromine? When octane reacts with bromine, one of the hydrogens is going to be replaced by Br, and then we're going to form an HBr. So we can see we have carbon 8, hydrogen 18. The product should be carbon 8, hydrogen 17, Br, plus HBr. Moving on. Question 8. A stream of liquid from a burette is deflected by a charged rod. We can see this is the burette, that is the charged rod, and we see the beaker to collect whatever is coming out. So they say which substance in its liquid state will be deflected the most. This deflection is about polarity, which one is going to be polar the most, or which molecule is going to have polarity. Looking at pentane, it's not polar. This one here is not going to be a polar molecule. The bonds could be polar, but the molecule is not going to be polar. In here as well, the bonds are polar, the molecule is not. The only polar molecule is this one here. So this is the only one that is going to be deflected the most, and therefore the answer should be a D. Moving on. Question 9. A piece of copper is shown. So this is the copper. How many molecules of copper atoms are there in a piece of copper? So they've given us the density of copper, which is 8.96 grams per centimeter cubed. My first step here was to find the volume. So this is a cuboid. It's easy to find this volume. It's going to be that times that times that, which gave me 384 centimeters cubed. Since I have the density, I can use the density and the volume to find the mass. We know mass is density times volume, which is 8.96, which is that times 384, giving me this as my mass. Now to find the number of moles of copper, it's going to be the mass of copper divided by the atomic mass of copper, which is 63.5. So dividing that, I got 54.1883 mole. Finally, to round off, my answer was 54.2 mole, and the answer here is D. Moving on. Question 10. Mass spectrometers are used in chemical analysis. In which region of this mass spectrometer are the ions accelerated? The ions are accelerated in the electric field, which is region Q, and so my answer is going to be B here. And in part B, they ask, for ions are present in a stream of ion in a mass spectrometer. The paths of these ions are shown. So we have path 1, path 2, path 3, and path 4, and they say which of these ions follow path 1 through the mass spectrometer. The ion following path 1 should be the one with the lowest mass to charge ratio because it was deflected the most. So among the 4 ions, I try to calculate the mass to charge. This is going to be 54 divided by 1, 54 divided by 2, so this is lower than that, so A is out. 56 divided by 1, this is higher than that. And 56 divided by 2, that is higher, so this is the least, and therefore the answer is going to be B. This will have the least mass to charge ratio. Moving on. In part C, naturally occurring chlorine has 2 isotopes. We have chlorine 35 and chlorine 37. How many peaks due to singly charged molecular ions are seen in the mass spectrum of chlorine? Now, since we are looking for molecular ions, there is a possibility of Cl2 being made out of 35 and 35, or Cl2 from 35-37, or Cl2 from 37-37. So the possible molecular ions are going to be 3. So the answer here should be a C. Moving on. Question 11. The graph shows the first ionization energies of some consecutive elements from period 2 and period 3 of the periodic table. The letters used to label the elements are now their chemical symbols. So you can see the graph has first ionization energy on the vertical axis and the atomic number on the horizontal axis. And the key thing here is they've told us these are consecutive elements. No matter which period they are in, whether 2 or 3, we count consecutively from one part of one period to the next part of one period. When we observe this, we can see this big gap in first ionization energy from Y to X shows that these are in an inner shell. The last electron of Z is going to have a configuration of 3s2. This is 3s1. So for X, we have 2p6 because they are consecutive, meaning from here we go direct to the inner shell, 2p6, 2p5, 2p4, 2p3, 2p2, 2p1. So down here they ask, which element has only one p orbital containing a pair of electrons? Only one p orbital containing a pair of electrons is going to be with element V. Writing the configuration, you can see it's going to be 2p4, and we have only one orbital containing a pair, so the answer should be element V. And next they say, which element is the least reactive? Now to answer this question, I try to display for you, these are groups. If we move from group 1 to group 8, and we know the last two electrons, these ones here, Y and Z, were in period 3, it means they must have come from group 1 and group 2. So assuming Z is group 2, this is group 1, and then here we have group 8, then all the way to group 3. This is going to be the least reactive because it's farthest in period 2, and these ones here are more reactive than these ones here because they have more shells. So we can say reactivity is going to decrease across the period, and therefore element X is going to be the least reactive. When we go to part C, they say which element has the greatest second ionization energy? When we look at element Y, it has one electron in the 3s1, but the next electron, which is the second electron to be removed, it's going to be in 2p6, meaning it's going to have the greatest second ionization energy, and so my answer here was element Y. Moving on. Question 12. A mass of 4.08 grams of hydrated copper 2 sulfate, which is that, was dissolved in the ionized water to form 250 centimeters cubed solution. What is the concentration of copper 2 sulfate solution formed in mole per decimeter cubed? So I formed the molar mass of copper sulfate or hydrated copper sulfate in this manner, and I got 249.6 gram per mole. Now the next part, since I'm given the mass, I wanted to find the number of moles, which is going to be this mass divided by the molar mass, and these are the moles I got. Remember, I'm looking for concentration in mole per decimeter cubed. So since I have the moles, we divide that by the volume, but the volume has to be in decimeters. So number of moles divided by 250 divided by 1,000 to convert it to decimeters cubed. I got that. In rounding off, I got 0.0654, which is close to that, and my answer is a C. In question 13, a mass of 2.50 grams of sodium chloride reacts with excess lead to nitrate solution, forming lead to chloride with a yield of 95%. What is the mass of lead to chloride formed? Since we were given the equation for the reaction, I just placed the information below each component. So 2.5 grams corresponds to this, and then we were told that this is in excess. So it means I'm going to use the number of moles of this because it's the limiting reagent. So moles of sodium chloride are going to be the mass divided by the molar mass, which is given here, and these were the number of moles I got of this that reacted. Now, I use the number of moles of this to predict the moles of this, and we know using the mole ratio of 2 to 1, so the moles of this are going to be half the number of moles of sodium chloride, which I calculated here, and that became my answer for the moles of lead chloride. The mass of lead chloride formed is going to be the number of moles times the molar mass, which is that times 278.2, and I got 5.9444385 grams. Now this mass is the theoretical mass of lead chloride. Now remember, we are looking for the actual mass, so since we have a 95% yield, percentage yield is going to be actual yield divided by the theoretical yield times 100. So 95 divided by 100 is going to give me the actual yield divided by the theoretical yield. Making the actual yield the subject, I got the theoretical mass times 95 over 100, and the answer came out as 5.65 grams. So A is my answer. So this brings us to the end of section A. Let's continue to section B. Question 14. This question is about barium and barium compounds. The graph shows the first 8 ionization energies of barium. We can see on the vertical axis we have ionization energy, and on the horizontal axis we have electron removed. The first question says, write an equation including state symbols for the third ionization energy of barium. Because this is the third ionization energy, we should begin with the Ba2+, meaning it's already 2+ charged, but it has to be in gaseous state. When it's ionized, it forms Ba3+, still in gaseous state, plus an electron that has been lost. In the next part, state how the graph confirms that barium is in group 2 in the periodic table. When we look at this, we can see it has the largest gap here between the second and the third ionization energy, so we can say that it's supposed to be in group 2. So I said its largest increase in ionization energy is between the second and the third ionizations. Moving on. In part B, an acidified aqueous solution of barium chloride is used to test for sulfate ions. They say draw a dot and cross diagram for barium chloride and show the outer electrons only. Now, because barium is in group 2, it could have lost the 2 outer electrons, so the present electrons are going to be 8 on the outer shell with a charge of 2+, and each of the 2 lost electrons is going to be gained by a chlorine atom to form a chloride ion, and I represented the 7 outer electrons on each chloride with 1 electron gained from barium, so you have to put a negative charge here. Please do not forget about the square brackets for all. This is ionic bonding. You have to represent them in square brackets with a charge on the outside. Next, they say, calculate the mass of barium chloride needed to form 150 centimeters cubed of barium chloride with a concentration of 0.2 mole per decimeter cubed. They want you to give your answer to an appropriate number of significant figures. So since I have this volume and this is the concentration, I began by calculating the number of moles. Number of moles is concentration times volume, which is 0.2 times 150 divided by 1000, and it gave me 0.03 mole. These are for barium chloride. Now the MR of barium chloride is also using your periodic table. Barium is that, and then the 2 chloride is going to be that. Adding everything up, I got this as the molar mass of the compound. Now the mass is going to be the number of moles times the molar mass, and it gave me 6.249. Rounding it off to 3 significant figures, I got 6.25 grams. Moving down here, they say the barium chloride solution is acidified to prevent carbonate ions giving the false positive result. Write the ionic equation for the reaction of hydrochloric acid with carbonate ions. State symbols are not required. So since this is hydrochloric acid donating H+, H+ is going to be reacting with a carbonate to produce carbon dioxide and water. So the rest was just balancing. Since we have 2 hydrogens, I put a 2 here. And again, in this case, state symbols were not required, so if you had not put them, you would still get 4 marks. In part C, give a reason why solid barium chloride does not conduct electricity. Because it's an ionic compound in solid state, they do not conduct electricity because the ions are not free to move. So I said because its ions are not free to move in solid state. So this brings us to the end of question 14. Let's continue to question 15. Question 15. This question is about hydrocarbons obtained from crude oil. Petrol used in cars has a high proportion of the alkane isooctane. Isooctane can be formed by heating octane to 400 degrees Celsius in the presence of a catalyst. So we can see octane as well as isooctane. And again, let me take away this so that you can be able to visualize. So here they say this is the compound which is isooctane. So they say give the IUPAC name for isooctane. Now to be able to name this successfully, you can see here we have 2 methyl groups on this carbon here. We have 2 methyl groups on this carbon, so it means I have to give that a lower location or a lower locant. So meaning this is going to be my carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. And again, choosing the longest chain to have 5 carbons. So that means there are 2 methyls on carbon 2 and 1 methyl on carbon 4. So my name is going to be 2,2,4-trimethylpentane. So in the next part, they say name the industrial process used to convert octane into isooctane. This is converting a straight chain hydrocarbon to a branched one. This process is called reforming. Give a reason why petrol needs a high proportion of isooctane. It prevents pre-ignition, or you could say it prevents knocking. Presence of isooctane promotes smooth combustion. You could also say it increases the octane number. Moving on. Here they say, another way to produce isooctane is by reacting isobutane with 2-methylpropene, which is that and that to form that. So they say draw the skeletal family of 4 isomers of 2-methylpropene, including only one isomer that does not decolorize bromine water. It means they want us to include an isomer that does not have a carbon-carbon double bond. Because this isomer is an alkene with a general formula carbon N, hydrogen 2N, the only isomer that will not decolorize bromine water should be a cyclic compound, because they also have the general formula carbon N, hydrogen 2N. So this is the first one. I positioned the double bond between carbon 2 and carbon 3. In here, the double bond was between carbon 1 and carbon 2. These two are geometric isomers. This is the cis version and that is the trans version. And then finally, I drew the cyclic compounds. It's either going to be that or it's going to be something similar to that. Moving on. In part C, 2-methylpropene reacts with hydrogen bromide to form 2 possible products. They say, draw the mechanism for the formation of the major product of the reaction between 2-methylpropene and hydrogen bromide. They wanted to include Kali arrows and relevant lone pairs and dipoles. So I drew the structure like this, and then since this is the carbon-carbon double bond, it's going to be closer to the HBr. We know this is going to be partially positive and that is partially negative due to the electronegativity difference, so this bond is polar. The double bond breaks donating electrons to the partially positive hydrogen, and this bond breaks heterolytically to form the bromide. And since they wanted us to form the major product, these had to become the carbocation so that we create a tertiary carbocation. In the next step, this carbon is going to gain a Br minus. Remember, you have to position the lone pair as well as the negative here as this one comes, and then we form my product, which is here. The next part they say, give a reason why your product in C1 is the major product. This is easy. The mechanism that led to the formation of this product went through formation of a tertiary carbocation. If the carbocation was here, it would have been primary and it would be less stable. We know a tertiary carbocation is more stable than a primary carbocation. So I said, because the intermediate had a tertiary carbocation which is more stable than a primary carbocation. In part D, another component of petrol, compound X, contains 92.3% carbon and 7.7% hydrogen by mass. They say, calculate the empirical formula of compound X. You must show all your working. So this is quite easy. I positioned the carbon and hydrogen and put their percentage by mass, which is that and that. Then to find the number of moles, I divided this by the atomic mass of carbon, which is 12, and I got that. To find the number of moles of hydrogen, I did the same, divide the percentage by mass with the atomic mass of hydrogen, which gave me that. Now to find the mole ratio, I divided that by that, and that by that, which is smaller. So I got the ratio 1:1, and the empirical formula should be carbon-hydrogen. Moving on. Here they say, a sample of compound X has a mass of 0.267 grams and vaporizes at 85.0 degrees Celsius and 104 kilopascals to produce a gaseous sample with a volume of 98.0 centimeters cubed. Calculate the molar mass of compound X. You must show all your working. So here they've given us PV is equal to nRT and the value of R is also given. So since I'm given the pressure, I converted this to pascals. So this multiplied by 1000 to get the value in pascals. And then I was given the temperature. To 85, I added 273 to get the temperature in Kelvin. And I was given the volume in centimeters cubed. So I had to convert that to meters cubed. I multiplied by 10 power negative 6 to convert it to meter cubed. So now using this formula and making n the subject, n is equal to PV over RT. I substituted for P, for V, for R, and then for T, and calculated to get the number of moles, which is that. Since we are looking for the molar mass, and I have the number of moles, it's quite easy. So molar mass is going to be mass divided by the number of moles. The mass is given here, divided by the number of moles, and I got 77.9 grams per mole. So down here they say, deduce the molecular formula of compound X using your answers to D1 and D2. Because my empirical formula was CH and the molecular mass is 77.9, this is going to be 12N plus N, which is 13N is equal to that. And when I divide it through and round it off, the closest answer is going to be N is equal to 6. So X should be carbon 6, hydrogen 6. So this brings us to the end of question 15. Let's continue to question 16. Question 16. This question is about the group 4 element, germanium, and some of its compound. Naturally occurring germanium consists of 5 stable isotopes. Explain what is meant by the term isotopes. Isotopes are atoms of the same element with the same number of protons, but have different number of neutrons, or you could say they have different atomic mass. The mass spectrum of a sample of germanium is shown. So we have the percentage abundance as well as the mass to charge ratios. So here they say calculate the relative atomic mass of this sample of germanium. And again, I divided everything by 100 just to show you, but you can just put one denominator and divide by 100 just one time. But I had to show because this is, of course, teaching. To find the relative atomic mass, I get the percentage, which is 20%. So 20 divided by 100 times the mass here, plus 27.4 divided by 100 times this mass, plus 7.7 divided by 100 times the mass, plus 36.7 divided by 100 times the mass, plus 7.6 divided by 100 times that mass. Now adding everything up, I got 72.703, which is 72.7 if I round off to 3 significant figures. The next part says, give the electronic configuration of germanium atom. Of course, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, and 4p2. So this is going to be the electronic configuration. Moving on. In part D, germanium is a compound with this formula. They say it can be formed by the reaction shown. So this is the reaction for that. Calculate the atomic economy by mass for the formation of germanium. They want you to use the atomic mass of germanium to be 72.6. Since we have the atomic mass, which is that, I wanted to find the molar mass of this compound, which is going to be 72.6 plus 4 hydrogens, and it gave me 76.6. So remember, when you're calculating atomic economy, we get the molar mass of the desired product divided by the molar mass of all products times 100. So this is the molar mass of my desired product. To find the molar mass of all products, I put that, which is already calculated, plus twice into the molar mass of sodium hydroxide. Sodium is 23, oxygen is 16, hydrogen is 1, plus the molar mass of this. Again, sodium is 23, boron is 10.8, and then oxygens are 2, which is 32. When I added that, I got 222.4. So in my final calculation for atomic economy, 76.6 is going to be divided by that and multiplied by 100, and I got 34.442. Rounding it off to 3 significant figures, I got 34.4%. And again, this is 3 significant figures, so I stuck with that. The next part says, germanium can donate a proton to ammonia, forming the ion, which is that. This is the reaction that occurs. They say draw a dot and cross diagram of the ion, which is that. Show outer electrons only. Because a proton has been donated, it means both electrons have remained. Meaning, hydrogen was bonded here. When hydrogen leaves as a proton, it means one extra electron that was from that hydrogen was left behind. So this is the electron that hydrogen left behind as it was donated to ammonia. And that means these 3 are going to be 3 bond pairs, and there is 1 lone pair. So I just showed 3 bond pairs, 1 lone pair, and put square brackets and put the charge on the outside. So down here they say, use your answer in D2 and electron pair repulsion theory to predict the name of the shape and the bond angle of the ion. So here, since we have 3 bond pairs and 1 lone pair, of course it's going to be trigonal pyramidal, and the bond angle is about 107, although they can accept 106 to 108. Here they say, germanium is toxic and the maximum permitted concentration is 0.640 mg per meters cubed in air. They want you to calculate the maximum number of germanium molecules permitted in a lab with a volume of 231 meters cubed. They've given you Avogadro's constant. So we know the permitted concentration is going to be 0.640 mg per meter cubed. How about in 231 meters? We can find the mass that is going to be in that, and the mass is going to be this concentration times the volume, and we get the mass. So it means in the 231 meters cubed, we'll have the mass of this in milligrams. But remember, we're going to calculate the number of moles, so I need to convert this to grams. And so I divided by 1,000 to find 0.14784 grams. Now, the molar mass of germanium is, of course, already calculated, 76.6 gram per mole from the previous page. So the permitted moles are going to be the mass, which is that, divided by the molar mass, which is this. and I got 1.93002611 times 10 power negative 3 mole. So we know the number of molecules is going to be the number of moles times Avogadro's constant, and this times 6.02 times 10 power 23, it gave me 1.161875718 times 10 power 21, and rounding off to 3 significant figures, but in standard form, I got 1.16 times 10 power 21 molecules to 3 significant figures. Moving on. Here they say, a halide of germanium, which is that, reacts with water as shown. 1.50 grams of this compound was added to excess water. So you can see here I wrote this is excess and this is the mass added. The insoluble compound formed was removed by filtration. The solution of hydrogen halide formed was then added to excess magnesium carbonate, forming this volume. Now this solution here is exactly this solution. It was reacted with excess magnesium carbonate, and the volume of CO2 produced, you can see, is that at room temperature and pressure, meaning we can use number of moles is volume of gas divided by molar volume. They've also given us the molar gas volume. So the first question asks, calculate the number of moles of carbon dioxide formed. Number of moles of CO2 formed are going to be volume of gas, which is that, divided by the molar volume, and I got 1.3979 times 10 power negative 2 moles. Then the next question says, deduce the number of moles of HX formed when this compound reacted with excess water. So I used the mole ratio, which is 1 to 2, meaning the number of moles of HX are going to be twice the number of moles of CO2, which is that times that, and it gave me 2.7958 times 10 power negative 2 moles. Then the next part says, deduce the number of moles of this compound that reacted with excess water. So in this case, because these moles are exactly those moles, I can work backward. These number of moles here are going to be 1/4 times the number of moles of this, which are exactly that. So these moles are going to be 1/4 times the moles calculated above here, which gave me 6.9895 times 10 power negative 3 moles. And lastly, they say calculate the molar mass of this compound and hence the identity of X. Because we have its mass and we have calculated the number of moles, it's quite easy to find the molar mass. Molar mass is equal to mass divided by number of moles, which is 1.5, divided by that, which is here, and then I got 214.6 gram per mole. This is the molar mass of this compound. However, they've also asked us to identify X. So to identify X, since I know the atomic mass of germanium, I can find the molar composition of X4. So what I did is 214.6 minus the atomic mass of germanium, which is 72.6. I got 142. But this 142 is for the 4 halides. I do not know which halides they are. So 142 divided by 4, I get 35.5. And therefore, we can conclude that X is going to be Cl, which is a chloride ion. So this brings us to the end of question 16. Let's continue to question 17. Question 17. Limonene is an oil extracted from the skin of citrus fruits, such as oranges or lemons. It is found in some cleaning products, such as those used to remove chewing gum. Limonene has the structure shown here. And again, for this, I'm going to first cut out this. So here they say deduce the molecular formula of limonene. The molecular formula is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. And then for hydrogens, I usually place them as I did previously. You can see these are the hydrogens per carbon so that we do not make a mistake. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the molecular formula is carbon 10, hydrogen 16. Next, they say a few drops of acidified potassium manganate 7 solution was mixed with a sample of limonene. State the color change. Because this is acidified potassium manganate 7, which has a color purple, when you react it with limonene, it's going to cause formation of diols, and so it's going to turn colorless due to the oxidation that has occurred. Next, they say, draw the skeletal formula of the structure of the organic product formed when the reaction in B1 is carried out with excess acidified potassium manganate. When we use excess acidified potassium manganate, all the carbon-carbon double bonds are going to be converted to single bonds, as OH groups are going to be formed around each carbon. So we'll form an OH here, OH there, and OH there. So my answer here is this structure. we can see 4 OH groups are going to be formed. Next they say, name the type of reaction that limonene undergoes in B1. In B1, we saw a reaction between potassium manganate 7, so that is an oxidation reaction. Moving on. So here they say, on heating, limonene reacts to form 2 molecules of a smaller hydrocarbon Q. Q can be polymerized to form R, a polymer used to improve the grip of car tires. A section of R is shown. This is R. So they say draw the structure of Q. We can see in this polymer there is a repeating pattern of this. You can see that is repeated again here. So it means the monomer is going to come from this. All we need to do is replace the double bond and cut away these extensions. As you can see here, this is structure Q. Then down here they say, give 2 ways in which chemists can help minimize problems caused by the disposal of polymers. Chemists could help by developing biodegradable polymers, or they could find ways of recycling or reusing some of these polymers so that they can be reused for the same polymerization process, or they could find safer ways to remove toxic substances before disposal of these polymers. Next they say, limonene is extracted from orange peel using a solvent. Possible solvents are hexane and liquid carbon dioxide. Liquid carbon dioxide can be obtained by allowing solid carbon dioxide to melt under high pressure. Suggest one advantage and one disadvantage of using liquid carbon dioxide rather than hexane to dissolve the limonene. Assume that the carbon dioxide does not escape in the atmosphere. So the advantage is CO2 is not flammable and CO2 can be reused because it doesn't escape. And then the disadvantage is CO2 has to be compressed, meaning a lot of energy is required for this compression process or to generate the pressure. In the next part, orange peel contains 1.63% of limonene by mass. A chewing gum remover contains 30 centimeters cubed of limonene per bottle. Calculate the mass of orange peel in kilograms needed to obtain 30 centimeters cubed of limonene. They've given us density of limonene is 0.841 gram per centimeter cubed. I began by calculating the mass of limonene per bottle, which is going to be the density of limonene times the volume per bottle. So here we have 0.841 times 30, which is 25.23 gram per bottle. Now we also know that 1.63 grams of limonene per 100 grams of orange peel. They gave us that information here because they said 1.63% of limonene by mass. It means it's going to be 1.63 of limonene divided by 100 of orange peel. So this is very important. Then it means we're going to have 1 gram of limonene per 100 divided by 1.63 grams of orange peel, which is going to be that. Then in the 25.23 grams of limonene, we're going to have that divided by 25.23 grams of orange peel. And then converting this to kilograms, I divided by 1,000 and I got 1.547, which is rounded off to 1.55 kilograms to 3 significant figures. So this brings us to the end of question 17. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.